Okay, so let us continue now with division inside the polynomial ring. So, as an example I did in the last video shows, we can divide as long as the polynomial has leading coefficient 1. So, just to give you an idea of what the problem will be, let us consider the following example. Let us take f to be 2x plus 1 and g to be x squared plus 1. So, they are both inside, let us say, the polynomial ring over the integers. So, now we can't divide by f. Why not? Because let us say you want to do the procedure that I did in the previous video. So, you will start with this, but now in order to get x squared from 2x, you will have to somehow cancel 2, but there is no way that you can do in the integers. So, you can't put anything here to get x squared here in order to cancel. So, you can't divide by f. The correct sentence is in the polynomial ring Zx. However, I claim we can divide by f in Qx, because we can get x squared here. Why is that? Because 2x when you multiply by 1 by 2 or x by 2 gives me x squared. So, now this existence of 1 by 2 is what makes this work, which exists in Q, but not in Z. So, we can divide by f in Qx. So, and what do we get? 2x plus 1. So, you get x by 2, then you get, it will be x squared here and it will be x by 2 here. So, now if you subtract, this will go away, this will be minus x by 2 plus 1. Now, to get minus x by 2, what you will do is plus 1 by 4, right, or minus 1 by 4 really, because you want to get minus x by 2. So, minus 1 by 4 times 2x is minus x by 2, minus 1 by 4 times 1 is minus 1 by 4, and you get so it is x squared minus 1 I am taking. So, let me change that. So, yeah, so it does not matter. So, it will be 1 by 4 plus 1. So, this is 5 by 4, right. So, this is the remainder, and remember remainder should have degree strictly less than the degree of 2x plus 1. In this case it is correct. So, degree is 0, correct. So, we can divide in Qx. So, in fact, the statement should be that we can divide by f as long as the leading coefficient of f is a unit. Okay. I described in the last video that leading coefficient has to be 1, but really it is not necessary that it is 1. The reason that 1 works is because 1 is a unit. So, that you can first get rid of these terms here. Okay. These terms here can be gotten rid of. So, it is not just when leading coefficient is 1 that you can divide as soon as leading coefficient is a unit. In the polynomial ring Qx, the leading coefficient of 2x plus 1, which is 2, is a unit. In the polynomial ring Zx, the leading coefficient of 2x plus 1, which is 2, is not a unit. So, you can't divide in Zx. And I want to write one more important property that is useful to keep in mind, and this example illustrates this. Suppose, so important property, so let us say Gx is an element of a polynomial ring and let alpha be an element of R. So, we can divide Gx by, we can divide right, because x minus alpha has leading coefficient 1 and this is monic. So, in any ring we can divide. So, I will always assume, remember, our rings are non-zero. So, we will assume our rings are non-zero. So, 1 is different from 0 in that ring. So, this is a monic polynomial. So, we can divide g x by x minus alpha, then the remainder I claim is simply g of alpha. Why is that? The reason for this is the following. So, reason. So, remember when you divide g x by x minus alpha, you will have some q x here plus some remainder, right. The remainder should have degree. So, and we know what are the properties of the remainder. Remainder is either 0 or degree of the remainder is less than the degree of x minus alpha, which is 1. So, in other words, the degree of R x is strictly less than 1 or R x is 0. Either way, R x is a constant polynomial, right, because we are dividing by a degree 1 polynomial x minus alpha, the remainder should be a constant polynomial. Now, let us look at this equation g x equals x minus alpha q x plus R x and substitute x equal to alpha. This is an important operation. So, if you have a polynomial identity, if you replace x by a specific element of the ring, you get an equation in the ring. So, if you substitute x equal to alpha, you get g alpha on the left hand side, alpha minus alpha times q alpha plus r alpha. Okay. So, now this is an equation in R. Now, x is gotten rid of, right. So, x is gone, what you are left with is actually an equation in R, but now alpha minus alpha is 0. So, this whole thing is 0. So, g alpha is R alpha, but note that we have already noticed that R x is a constant polynomial and g alpha is R alpha. So, R x must be just g alpha, because you have a constant polynomial, it does not depend on x, and at alpha it is R alpha, means it is g alpha. Okay. So, this tells me that when I divide by a linear polynomial x minus alpha, the remainder is simply the value of the polynomial when you evaluate x equal to alpha. And if you go back to this example that I did in the beginning of today's video, here I am doing x squared in the above example. In the above example, g x is x squared plus 1 and we are dividing by x minus, or rather we are dividing by 2x plus 1. Now, we need to write this like x minus alpha. Okay. So, I can't quite write this, it is not of the form x minus alpha, but we can multiply this by a unit. So, 2x plus 1 times 1 by 2 becomes x plus 1 by 2, which can be written as x minus 1 by 2. So, the important point when you are dealing with the division in polynomial rings is you can always multiply the polynomial by a constant, remainder does not change. So, here division by 2x plus 1 is really division by x plus 1 by 2, which is x minus 1 by 2. So, the remainder by the property that I wrote earlier should be g of minus 1 by 2, right. G of minus 1 by 2 is minus 1 by 2 squared plus 1, which is 1 by 4 plus 1, which is 5 by 4. And remember, this is exactly the remainder that we got, right. The remainder is simply evaluating the polynomial at minus 1 by 2. So, this is always true when you are dividing by a polynomial of the form x minus alpha, what you get is simply g of alpha. Okay. So, this is useful to keep in mind. The next, so this is our discussion about polynomial ring in one variable, because I want to introduce now polynomial rings in several variables. But just to recap what we have done, we have introduced polynomials in a single variable x. X is really a symbol, its expressions as powers of x with a coefficient coming from r in front of it, and then we learned how to add them, we learned how to multiply them, and we observed that it becomes a ring. Next we learned how to divide polynomials. While division is not always possible, we can always divide as long as the leading coefficient is 1 or unit more generally. So, now we want to talk quickly about polynomials in several variables. Okay. So, this is we will not discuss a lot at this point, because this will come up later for us, and at that time I will say more, but at this point I will just want to quickly tell you what I mean. So, several variables means more than one variable. So, we will again fix a ring R, and now we fix variables or symbols, let us say n of them, x1, x2, xn, okay, and we want to consider r square bracket x1 up to xn. Earlier we had r square bracket a single variable x, and now we have n variables. So, these are going to be polynomials in x1 through xn with coefficients in R. Okay. So, just like in the earlier case when you had monomials of this form, right, we had monomials of this form in the one variable case. What we will now have is in so here we will have, let us say I will not write n because I have used it n here. So, this is one variable case. If you remember, a polynomial is made up of terms like this, we add several of them together. Here multivariable polynomial will be made up of terms like this. So, you will have a I1, I2, In. So, this will be a subscript, okay, with these n indices, and we will have the variables will be x1 I1, x2 I2, xn In. So, this is the n variable case. Okay. So, in n variables, these are the monomials. So, this is a single monomial. Okay. Now, a polynomial will simply be several of these added together. So, as an example, let us take n is 3. So, you have x1, x2, x3. What is a polynomial? So, here we will write f1, f of x1, and let us say I am looking at z x1, x2, x3. So, f x1, x2, x3 will be, example of such a polynomial will be, let us say 3 x1 squared x2 cubed minus 6 x1 squared x2 cubed x3 5 plus x1 squared x3 power 8 minus 8. I am just randomly writing something. So, several such things together. So, now each monomial has a degree attached to this. This is like 2 3 0. So, it is a triple. This will be 2 3 5, this will be 2 0 8, this is 0 0 0. So, now we can add and multiply as before. It is exactly the same process as before, slightly more complicated looking, because now we have to keep track of degrees as tuples. So, if you add two polynomials in 3 variables, you have to compare like terms. So, like term will be things which have x1 squared x2 cubed. In the other polynomial, you will see if there is such a term, and then you compare, you add the coefficients. multiplication is the same. How do you multiply? Again I have to only tell you how to multiply two monomials. So, let us say we have this and this. How to multiply them? I will simply multiply the coefficients because they are elements of R, and exponents I will add just like before. So, I 1 plus j 1 x 2 power I 2 plus j 2 all the way up to x n power I n plus j n. Okay. So, this is multiplying a single monomial with another single monomial. Now, how to multiply arbitrary monomials? You will simply one by one you multiply, just like you did in the case of single variable polynomials. So, this is just to give you an idea of how to multiply and add two multivariable polynomials. So, now one final comment about this, just like we have not verified that, but it is an easy fact to verify. Single variable polynomials form a ring. Here also R x one okay. So, this is a polynomial ring. So, this is a ring rather I should say first. So, polynomials in n variables with the addition and multiplication that I briefly described is a ring called the polynomial ring in n variables over R. So, earlier we talked about one variable polynomial ring. So, now we have a polynomial ring in n variables over R, and one easy way to think of this, for example, let us say two variable polynomial ring I want to consider. So, R x 1 x 2. So, these are polynomials in x 1 and x 2 with coefficients in R. I want you to convince yourself that this is actually nothing but R adjoined x 1 first. So, this is a ring, right, this we discussed earlier, and then you do x 2. Because we have talked about polynomial rings over any ring, I can take this ring and consider polynomials over this ring in one variable. The new variable I will call x 2 because x 1 is already used. There is no difference between these two things. Here the terms are of sums of this kind, right. So, a I 1 I 2 x 1 I 1 x 2 I 2. So, you take a monomial like this and you add several of these together to get an element of this. What would be things here? Things here will be x 2 power I, but the coefficient would be a polynomial in this, right. So, now if you break up f x 1 as a sum of monomials in x 1 and multiply by x 2 I, you will get this. So, they are really looking at the same thing in two different ways, and the advantage of thinking it in these terms is this is a process that you already understand, because earlier we have discussed, given a ring R, how to construct a polynomial ring in one variable, and that is exactly what I have done here. Okay. So, in order to understand polynomial ring in two variables, all you need to understand is polynomial ring in one variable over polynomial ring in one variable. So, similarly, if you want to understand what is x 1, x 2, x n polynomial ring in n variables, this is nothing but you first consider the polynomial ring in n minus 1 variables and you add one variable. Okay. So, this is just adding a polynomials in a single variable called x n with coefficients coming from x 1 polynomial ring in n minus 1 variable. So, these are coefficients. Okay. So, and again as I said, these are exactly the same objects, but our view is different, our perspective is different, and we will not initially at least discuss much about polynomial rings in several variables, but I wanted to discuss at least define them so that you are familiar with it. I am going to end this video here. In the next video, we will continue with our study of rings and we will study homomorphisms and ideals and so on. Thank you.